In this class, we're going to extend our work on series of numbers to series involving a variable, and these are called power series. So this is a brand new thing that we're looking at. It's an infinite sum, which is what we've been studying for the past several classes. But all of the infinite sums we've looked at before today were just numbers, a number plus a number plus a number plus a number, and it goes on forever. So now we have this infinite sum, and there's a variable in there, x. So first thing I want to do is write this in closed form, which means use sigma notation. So I want to look at each term, and if I put the hidden exponent and denominator on that first term, it's a little bit easier to come up with the standard form. So every single term has an x minus 2 to a power. So I'm going to start with x minus 2 to the power of n, because the first term's the first power, the second term's the second power, the third term's the third power. So if I start, my sum is going to start with n equals 1 and go to infinity. And every single term has an x minus 2 to the nth power. The first, and then the second, and then the third. And then what is the denominator? How is it related to n? N squared. This is 1 squared, 2 squared, 3 squared, 4 squared. So my denominators are n squareds. And then I have to deal with the fact that these signs are alternating. I have positive, negative, positive, negative, positive, negative. And alternating signs we usually handle by doing -1 to a power. So I'm going to do -1, and then I have to decide what power to put up here. If I put an n, my first term would be negative, right? Because it would be -1 to the first. But my first term is positive. So what should I put up here for n? N plus 1, yeah. Because then when I plug in 1, I'll have a -1 squared. My first term will be positive. So that's my closed form, sigma notation, for the infinite sum that we wrote up above. So before I move on to the next question, I want to just sort of explore this a little bit. This is a function, right? My x is a variable that I could replace with a number. So I'm going to name this like p of x. P for power series. Or polynomial, right? The powers are going up by 1. Okay, so let's just look at what is, say, p of 3. That means replace all the x's with 3's, right? So 3 minus 2 is 1. 1 to the first over 1 is 1. And then I have a minus, and then 3 minus 2 is 1. 1 squared is 1 over 4. 3 minus 2 is 1. 1 cubed is 1. So I have 1 over 9. And then minus 1 over 16. That's an infinite series that we're familiar with. What can you say about that series? It converges. How do you know? Perfect. Yes, the terms are decreasing towards 0 and the signs are alternating. So this converges by the alternating series test. So that's what happens if you plug in 3. Let's do another one. Let's plug in 6 or 4. Let's plug in 4. It's a little easier. I just need a little more space here. So p of 4. 4 minus 2 is 2. Minus 4 minus 2 is 2. Squared is 4. So 4 over 4 is 1. And then 2 cubed is 8. So I have 8 over 9. Minus 2 to the 4th is 16. Over 16 is 1. And then let's do a couple more. 2 to the 5th is 32. 32 over 25. And one more. 2 to the 6th is 64 over 36. So what do you think about this series? Where am I missing a minus? Nope, I don't think so. I'm plugging in 4 into each of these terms. So these two happen to come out to -1, but that doesn't mean you're going to get a -1 every other term. Are those terms decreasing towards 0? (32/25) and then 64/36. Which one is bigger, 32/25 or 64/36? 64/36. These terms are not decreasing towards 0, which means that this diverges by the nth test for divergence. Okay, so this function, p of x, it's an infinite series. Sometimes it converges for some x's, and for other x's it diverges. So a natural question that's going to arise is what x values make it converge and what x values make it diverge. So we're going to use the ratio test to determine the interval of convergence. The interval of convergence is an interval of x values for which your series converges. It's going to give me a whole range of x values that will make this converge. So we start with the ratio test, and the ratio test is done by calculating a value L, which is the limit as n goes to infinity of the absolute value of the n plus first term over the nth term. So that means take every single term, every single n, and you're going to replace it with an n plus 1. So it's helpful to have the sigma notation version handy, because you're just going to replace every single n in the formula with an n plus 1. So this is the limit, and then goes to infinity. Okay, the n plus first term. So if I replace that n with an n plus 1, I've got -1 to the n plus 1 plus 1. Just replacing this n with an n plus 1. So you have n plus 1 plus 1. And then times x minus 2 to the n plus 1 over n plus 1 squared. So every single n in the closed form formula gets replaced with an n plus 1. Then you're going to divide by the nth term, which means just copy the exact closed form formula underneath. So divided by the nth term, which is -1 to the n plus 1 times x minus 2 to the n over n squared. Okay, so to simplify this compound fraction, I'm going to flip and multiply. Take the bottom fraction, flip it, and multiply it. So I'm also going to simplify this a little bit. So I have -1 to the n plus 2 times x minus 2 to the n plus 1 over n plus 1 squared times, and then flip and multiply. So I've got n squared over -1 to the n plus 1 times x minus 2 to the n. Now I want to simplify in the parentheses as much as I can. Okay, so something to the n plus 2 over something to the n plus 1. The same something, -1, right? But like the same base, dividing like bases, you subtract the exponents. N plus 2 minus n plus 1 is 1. So it's just a -1, and it's going to go in the numerator. -1 to the first. And then x minus 2 to the n over x minus 2 to the n plus 1 over the nth, right? So dividing like bases, subtract the exponents. N plus 1 minus n is 1. So I have an x minus 2 in the numerator. And then I still have times n squared over n plus 1 squared, which I'm going to multiply out. N squared plus 2n plus 1. Those you can't cancel anything because you can't cancel the n squareds because the n squared is separated from the 2n by addition. All right, so I'm taking the limit of n. So the only thing that's sort of changing in here is n's. So x minus 2 I can treat as a constant. So I can take the x minus 2 out of the limit. But this is actually absolute value. So I'm just going to do a real quick limit as n goes to infinity. Take the absolute value of each piece. The absolute value of -1 times the absolute value of x minus 2 times the absolute value of n squared over n squared plus 2n plus 1. All right, what's the absolute value of -1? 1, so that I can just ignore. That's just 1, right? And then x minus 2 I'm going to treat as a constant. I'm taking the limit as n goes to infinity. That does not, there's no n's involved here, so I'm going to pull that out of the limit. So I get the absolute value of x minus 2 times the limit as n goes to infinity of n squared over n squared plus 2n plus 1. Okay, what is the limit as n goes to infinity of n squared over n squared plus 2n plus 1? 1. They have the same exponent, so it's the ratio of the leading coefficients. So this is the absolute value of x minus 2 times 1. So that's the beginning of the ratio test. The ratio test says take the ratio of the leading of the an plus 1 over an in absolute value, limit as n goes to infinity, and then what does the conclusion tell us? The ratio test says that that limit has to be, look it up, less than 1. Okay? That the series will converge if that ratio is less than 1. So I need to force this. I have to know what x's will make this ratio be less than 1. And that will tell me what x's will make it converge. Okay, so I need to solve the absolute value of x minus 2 is less than 1. So this gets converted to a compound inequality where you have -1 is less than x minus 2 is less than 1. Because if the absolute value is less than 1, then that means that the opposite of the thing has to be bigger than -1. We are saying that for convergence, this has to be less than 1. Yes. Yeah. So it's not necessarily always less than 1. We're just saying, okay, to get convergence, we need that ratio to be less than 1. So I'm going to solve what x values give me a ratio less than 1. So now I just add 2 to all 3 sides of this equation. So we get 1 is less than x is less than 3. This is called the interval of convergence. Okay, for x values between 1 and 3, the p of x sum converges. Now, what did the ratio test tell us when you get equals 1? You can't tell anything. So you have to test the endpoints separately. You do a whole separate test where you plug in the endpoints. And we earlier, in one of our examples, I plugged in 3, which was which is one endpoint from 1 to 3. So when you plug in 3, we got convergence. So I know that 3 also causes convergence. So my interval of convergence here, 1 less than x less than 3, I'm going to put an or equal to on the 3 because I know I get convergence when x equals 3. I'm going to test the 1 separately too. I have to plug 1 into my series. Get a new page here. So my series was x minus 2, p of x equals x minus 2 minus x minus 2 squared over 4, x minus 2 cubed over 9, 4th over 16. Okay, so there's my series. I'm going to test the endpoint of 1. I know that everything between 1 and 3 will cause convergence. I have to test the 1 and the 3 separately. So I already did the 3. We got convergence. So when I plug in a 1, I get 1 minus 2 is negative 1. Then I get negative 1 squared, which is 1. So I have minus 1/4. Yep. And then if I plug a 1 in here, 1 minus 2 is negative 1. Negative 1 cubed is negative 1. And then if I plug a 1 in here, I get negative 1 to the 4th, which is positive 1. So I have minus 1/16 minus dot, dot, dot. So what happens here? What do you think? Convergence or divergence? No thoughts? They're not alternating. You can't use the alternating series test. Use the absolute convergence test. Yeah. So if you take the absolute value of all these terms, you get a p series that we know converges. Yep. So I'm not going to write out all the details, but I'm just going to say this converges by the absolute convergence test. You could also just factor out a negative 1. You could just say negative 1 times 1 plus a 4th plus a 9th plus a 16th. You know, that converges because it's a p series with p greater than 1. So that's a finite number. Finite number times negative 1 is still a finite number. So this converges. So that means that 1 is also part of my interval of convergence. So I'm just going to go back to my previous slide, and I'm going to include the 1, the endpoint of my interval. So those are all the x values that will make that series converge. Plug in anything from 1 to 3, including the 1 and the 3, you'll get convergence for that power series. Okay, so this last bit is just a little vocabulary. So a power series about x equals a is a polynomial with infinitely many terms that looks like this. You've got some unknown coefficients. You've got about x equals a means you're doing x minus a for all of your terms. And then you've got the powers increasing by 1. And the interval of convergence for this thing is always centered at a. And we call the distance from a to an endpoint of the interval of convergence the radius of convergence. So for our example, the interval of convergence was negative 1 less than or equal to x less than or equal to 3. Another way of writing this is interval notation 1, 3. If you draw 1 to 3 on a number line, here's 1, here's 3, 2 is right in the middle. 2 is the center of the interval of convergence. That's why we say the power series is centered at A. So this A value in our case was 2. It's the center of the interval. And then the distance from the center to an endpoint is the radius of convergence. So this is your radius of convergence. In our case, it's 1. So 2 is the center. Radius is 1. So that's it. Just keep in mind that the endpoints of your interval always need to be checked separately. The ratio test is inconclusive when that limit equals 1. So you have to test the endpoints on their own using tools from the past few sections.